So we're going to... Nice. That's staying in there. I'm not editing that. So we're going to talk about constant velocity, constant acceleration, okay, and constant distance. This set of graphs we're going to build, okay, but I want you to understand what this looks, what's going on here. And it looks a little messy, but there's organization, there's structure. If you'll notice, I have 3 by 3. Okay, I've got 3 by 3. I have in each column, I have the same distance versus time graph in the first column. In the second column, I have velocity versus time. You guys see that? And here I have what we're calling acceleration versus time in these 3. Okay. Horizontally, I have one of each of those graphs, and horizontally, I'm going to call out a specific state. In this first row, we have constant distance. Okay? In the second row, we have constant velocity. But all the graphs are the same for that current state. So for the first 3 graphs, all 3 graphs represent constant distance. The second 3 graphs represent all of them at constant velocity. And the third set of 3 graphs, all of them are showing constant acceleration. Okay? So let's start with the basic one, constant distance. What does constant distance, what does the word constant mean?
Stays the same.
Stays the same means that there's no change. Delta whatever equals what? Delta whatever equals 0 if it's constant, right? You can write them down if you want to see them, but I'm going to go one at a time. You might sort of, if you draw them as I go through them, they'll make sense, okay? I will give this to you, but you probably should draw this, okay? So if I have constant distance, if I have a constant distance over time, what does that mean? If I have a constant distance over time, what does that mean?
You don't move.
No distance change, which means I don't move. This is constant distance. Time is ticking on, and I'm not moving. So from a graph standpoint, distance versus time, okay, I have the same distance. I haven't moved. I'm in the same spot. This is not plotting the change in distance. This is plotting the specific distance I'm at, or the position that I'm at. Does that make sense? Okay. If, however, I have, and what do we know? What do we know about velocity? What is velocity? What did we decide? What did we determine velocity was the other day?
The distance over delta time.
Okay. So if I have a velocity, a graph of velocity, right? I'm going to have a specific change in time, and at each change in time, I'm going to have a delta distance, right? So I have a delta distance and a delta time. And the velocity is represented in a distance versus time graph as what? What thing? What mathematical, geometrical thing? Slope, right? So the slope, and what do we say slope is? Slope is equal to generally what? Rise over run, right? So in this distance versus time graph, what's my rise? In this distance versus time graph, what's my rise of my slope? Delta D, or my change in distance. Okay, I'll change the color. So it's my, sorry. Okay, so my slope is equal to my rise over my run. And what's my rise? Delta D, right? Delta distance. Okay, what is my run?
Delta time.
Delta time. Okay, and what did we define, by the way? And so we defined this ratio as what thing? What did we define this as yesterday? Or on Wednesday? Did we define this? Yeah, we defined this. Delta distance over delta time is what thing? Velocity. Yeah, we did. So let's look. That's why I'm going over it again. Velocities are change in distance over change in time. By the way, delta distance, what is the actual delta distance? What's the equation for delta distance? I talked about this on Wednesday. What is it? What is it?
Velocity times delta.
No, but it is. But okay, yes, but without using time, just a straight delta D. What is just straight delta D? Final minus initial. Our distance final minus our distance initial. Right? And if we say over delta T, what's our delta T equal to? What's delta T equal to?
Time final minus time.
Right, time final minus time initial. By the way, how do I know that my distance, how do I know, let's say I call this point A and point B. Which one is my final point, A or B? Which one's my final point, A or B? It's B. So my final point is what? B. Why is my final point B? What determines it as my final point? Huh? Later or time. This is very important. Yes, ma'am.
Oh no, I'm told.
Oh, okay. What determines what is final is what happens later in time for the 2 points I'm looking at. This is it's fundamental, but very important. You're like, oh, duh, but it's very important. What determines the final is, if this is my time initial, this must be my time final, because time final always comes after time initial, because time always moves forward. It does, unless you're a wormhole. All right. Okay, time will always move forward, guys. Time will always always move forward. Now, okay. That's my velocity, guys, right? Okay. Now, I'm gonna do another graph, okay? This graph is going to look very similar to my graph I just did, except now rather than having distance in time, I have velocity in time. Okay, let's just draw this here for a second. Let's do this. Here's my distance in time, and let's say that we have this. This represents here that I have a what? On the distance versus time graph, what is it? Well, what is it? Okay, but what is it? It has a velocity. And what kind of velocity?
Constant.
Why do you know it's constant?
Because it's a straight line.
It's a straight line. The slope is always the same no matter where you are. How do I draw a constant velocity on a velocity versus time graph? Horizontal straight line. Yeah. Okay. Why is it constant velocity? What does constant mean? No change. Here's my velocity. It's my velocity here is v1, right? V1, right? Does the v ever change as time goes on? Right. So I have constant velocity. Does that make sense? Everyone with me?
How do we compare? They're the same.
They should be the same, right? Look,
Different.
distance in time, velocity in time. I had a slope here, right? My slope delta distance over delta time. What's delta distance over delta time? Velocity. If this slope never changes, right? By the way, is this delta D and delta T? Let's say delta D1, delta T1, delta T2, delta T2. So it's delta D1, delta T2, delta D2 over delta T2. Are those things the same or not? Why? Okay, good. I want to make sure we're clear on that. It's constant, it's the same. Constant slope means the slope doesn't change. The ratio is always the same, right? It's the same triangle, they're just similar, right? If I have a constant velocity, means my velocity does not what? And therefore, my velocity as time moves on does not change. This is like I'm driving a car at 30 miles an hour on a straight road, and I have the cruise control on. Okay? Means I'm going 30 miles an hour on a straight road, I'm going one direction, I'm going 30 miles an hour, and I'm not changing the speed. That's what this represents. If I took a turn, here's a quick side thing. We'll deal more with this later. If I'm on that road, I'm going 30 miles an hour, cruise control is on, and all of a sudden the road turns and I turn. Do I have constant velocity? Why not?
Because you slow down.
Hold on, what?
So you increase or increase for the turn.
No. Let's assume that my speedometer stays 30 miles an hour through the turn.
Because your distance went down.
No. Well,
It took more time for the turn.
no. Because I'm traveling the same distance and time. My distance, I still travel 30 miles in an hour, even if I'm going in a circle. But what's changing? Well, in a different way. But what? If I'm going, not the direction. My direction changes. A velocity is not just my speed; it's a speed and a direction. And if my direction changes, then I actually have a change in my velocity.
So how do you add that to the...
We'll deal with that later. But I just was going to make a side note, okay? But for the moment, if I have a constant velocity, that's what the constant velocity looks like. So I go back to my graph. And I say, look, here's my constant distance over time, or constant velocity and distance versus time. Here's a constant velocity and velocity versus time. You guys see that? So we're all clear with this, right? Because I can ask you, draw me on a distance versus time graph, constant distance, constant velocity, and so forth. All right, so be prepared. Make sure we understand this. And now we'll do this in a minute. Okay, now I'm going to do one more thing. I'm going to take this and I'm going to shrink all of this down. Whee! Okay. And I'm going to now go ahead and take another graph. And I'm going to do another thing here. Here is my, actually I'm going to do this. Let me take this up, move this up here. Okay. Okay. So now I have my velocity versus time graph. Okay. And now, actually, let's say that I had, let's say rather than having a constant velocity, let's say my velocity was changing, but in a constant manner. Okay. Remember that velocity, the velocity is equal to my change in distance over my change in time. If I look at it from a unit standpoint, what's my standard unit measurement? Meters. And my standard time measurement? Seconds. So it's a meters per second, right? And if I have no change in velocity, so my delta V in this case is what? 0 meters per second. No matter what my time is. In this case, what's happening, I've got point A and point B. What am I doing?
Slope constant.
I have a slope and it's constant. I have a slope of delta V.
Oh my god, I'm sorry. Okay,
Okay, put that away, please. Yes. Okay, I've got a delta distance and a delta velocity. Here's my delta V. Here's my delta T, right? You guys clear with this, right?
What about distance?
In this case, but now I got velocity versus time. I originally was saying here's velocity, constant velocity, velocity is distance over time, meters a second. I say, well, if I have in this case, I have no change in velocity, therefore my change in velocity is 0 meters per second, right? However, now I'm going to draw a curve in velocity versus time where my velocity is going to change. Okay? If my velocity changes, what does it mean I'm doing? Okay. I'm either speeding up or slowing down, or what do we call it is what? Okay. So the delta V over delta T is what we call acceleration. Okay? Let's say you're at a stoplight. What speed are you going? What's your velocity? Light turns green, what do you do? What do you physically do?
You press the gas.
You press the pedal, what's it called? The gas or the accelerator. So it's going to accelerate you. And what do you notice about your speedometer? What is it doing? Going up. Are you when you hit the accelerator and hold it, are you traveling at a constant velocity?
Well, no, you're going like a bend. If you're like going
Whoa. You're at a stoplight and you're trying to get to 60 miles an hour. You press the pedal. and your speedometer is moving up, are you traveling at a constant velocity?
If it's going up, no.
Then no. If the speedometer is going up, then no.
But if you're increasing at the same rate, then you're accelerating.
Constant acceleration. This is exactly the conversation we have to have. There's a difference between constant acceleration and constant velocity, and they're not the same thing. If I have a constant velocity, I have how much acceleration? 0, because that means my velocity is the same. Constant velocity is cruise control. Am I accelerating? No. Constant acceleration is a constant change in velocity. I'm speeding up over time. As time goes on, you have to start looking at this. This graph is not about distance. This graph is now about your speed. You're plotting your speedometer here, not your position. This is 30 miles an hour. This is 60 miles an hour. This is 0 miles an hour. You follow me? So you're increasing your speed as time goes on. Your speedometer is moving up. That's acceleration. Okay? Does that make sense?
You do that on a velocity graph.
Velocity versus time. Because I'm changing my velocity. If I was not changing my velocity, if I'm on cruise control, what does it look like? A straight horizontal line. This is cruise control. This dude here is pedal to the metal. Okay?
Cruise control is constant velocity.
I'm sorry?
So cruise control is constant velocity. The little yellow line, which is pedal to metal, is changing velocity.
And it's a change in velocity. And if my change in velocity over time is always the same amount, let's say in 1 second I go from 0 to 30 miles an hour. And the next second, if I'm constantly accelerating, after time 2 seconds, what should be my velocity? Right, because I'm changing 30 miles an hour every second.
So it's constant acceleration.
Yes, exactly. So at that point, okay?
So can you have both at the same time?
No, you can't. So this here is pedal to the metal.
So it's just different graphs, pretty much.
Exactly. These are different graphs of the same thing, but I'm trying to show you the relationship. This is how much acceleration? 0. So this looks like this. Constantly 0. Here is constant acceleration if the slope is the same. And whatever this value right here, this A right here, this value of A is my slope. Right? Whatever my slope is, that's my A. Actually, let me do it this way. My A, the A value is my delta V over my delta T. Whatever that slope is, that's the value of this. If I have a shallower slope, where does this line go? Lower. If I have a steeper slope, where does it go? Higher. What does this graph mean? What do these two graphs mean about my speed? It's increasing. Okay. Correct. Here's a question. Yes. Let's say I have a negative acceleration. What does that mean that I have a negative acceleration? Wait. I'm going to pick. Don't take the defenses, but say it again. No, you can't. You said you were going backwards, right? Is that really correct? Let's think. No. This is a common misconception. It's okay. Don't cry. No. There's a common misconception. It's a jump because it's this issue. If I have a negative acceleration, does it necessarily mean I'm going backwards? It can mean that, but it doesn't necessarily mean that. It means if I have, as I'm going 60 miles an hour, how do I have a negative acceleration? What do I do to my car? How do I get my car to decelerate? How do I get it to slow down?
You have to take your foot
Off the gas and do what? Hit the brake. So if I'm going 60 miles an hour, okay, I'm going 60 miles an hour, I want to decelerate, okay, or lower my velocity, I have to hit the brake. And now I start to slow down. Whoa, 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 you've got too much stuff going on. Carmen?
I said negative velocity is when you're going backwards, right?
No, I have a negative change in velocity.
Okay, that's what I meant.
Okay, if I have 60 miles an hour, over time I'm going to go down to 50. I'm still at the forward velocity, but I have a negative change, which means I have a negative acceleration. Okay? Think about this. If acceleration is a change in velocity or change in time, is my change in time ever going to be negative? What does the change in time equal, guys?
Time is always like...
What is delta time is equal to what thing? Delta time is equal to what minus what?
The initial time. No, the final time minus initial.
Final minus initial. If time always moves forward, will delta t ever be negative? No. So the denominator will always be positive. But if I start at 0 miles an hour and go to 50 miles an hour, my delta v will be what? Positive or negative?
Negative.
Positive. Therefore, my acceleration will be what? Positive. If I'm going from 50 miles an hour down to 30 miles an hour, what's my change in velocity? But what sign is it? Negative. If I start at 50 and I go to 30, my final is 30 miles an hour. My initial is 50, so 30 minus 50 is negative 20. Negative 20 over delta t, negative over positive is a negative acceleration. Do you guys see that? I'm decelerating. Yes? Okay. I want to do, let's look, now that we've done the skateboard bit, and you have a feeling for constant velocity and constant acceleration, Lauren, phone away, please. Okay? Now we're going to look at this graph. So now we have this constant velocity, d versus t and v versus t. Right? You guys see that? Is that clear? Now here's this scenario here. We've got a constant acceleration where we have a straight line in acceleration versus time horizontally, and we have a straight angled line for velocity versus time. Does that make sense? Are you with me? Okay. So, and you'll notice that distance versus time is actually a parabolic. We'll get into why that is in a minute. Okay. It's a parabola, but there's a reason why it is. Okay. Okay. Oh, I didn't mean to do that. Oh, well. Open. Okay. So, any questions on this stuff so far? No? Okay. Okay, so what we're going to do is we're going to talk about velocity and time, okay? Oh, before I do, let me do one thing. If I had acceleration in time, okay, and I say, yeah. And my acceleration is equal to delta v over delta t, right? And our delta v, our velocity is equal to delta distance over delta time, right? Okay? This is meters per second, right? Our change of distance is meters, change of time is second, right? In this case, I have a meters per second over second. So this means this is equal to meters per second times 1 over second. Meters per second squared. Woo! Kaboom, right? Does that make sense? You see this? So from a unit standpoint, these are our units. Acceleration and velocity. Does everyone see that? Okay. Now, if I had, let's say I changed this graph. Let's say I changed this graph, and I made this a velocity versus time graph. Oops. Okay. And let's say that I was traveling at, let's say, guys, I was traveling at 30 meters per second. Okay. And let's say I traveled, oops. Let's say I traveled for 10 seconds. How far did I travel? I was traveling 30 meters per second for 10 seconds.
Oh, you 30 up there.
Okay. So if I looked at, let's look at this. Let's say I did it for 1 second. How far have I traveled? For 2 seconds, how far have I traveled? 60, right? And so on. So what you're saying is you're saying, look, I've got traveled 30 meters per second times what? 10 what? Over 1. And that means, because in the end, if I'm asking you what the distance is, what's my delta distance? What's my velocity times my time? And I'm going to cancel my seconds to be left with meters. So you can do this a couple of different ways, but unit analysis is really important to help you think about what you're going to end up with and how to, if you're confused as to what equation to use and how to do this. So I can say 30 times 10 is what? 300 meters over seconds have canceled, 1. So what I've done is I've said, well, my delta D is equal to my velocity times my delta T, right? Well, really, isn't V equal delta distance over delta T, right? Isn't this the exact same thing? Okay, so that's what you've done. Well, let's look at this for a second. So you said that, look, I was at a velocity of 30 meters a second for a time, a delta time of 10 seconds. Well, wait a minute. What is this shape here?
Rectangle.
Rectangle. What's the area of a rectangle?
It's
Base times height, right? What's the height here?
30.
30 what?
Meters per second.
And what's the base?
10.
So our delta distance in a velocity versus time graph, our delta distance is the area under the curve. Do you guys see that? All right. And if you think that blew your mind, just hold on. Wah, wah, wah. I hate when this does it. Hold on. What did you just say? Oh, look at you. All right. Oops. So let's look at this and we'll say, all right, now, let's say, and by the way, what was this showing? This is showing what? Constant what? Constant velocity, right? Okay. Here's my velocity. Oops. I keep doing that. Here's my velocity and my time. Okay. And now let's say I have a constant velocity this way. Okay. And let's say I go for, again, a specific delta time. Okay. What is the, if we know that the area under the curve is our delta distance, right? What's the area under this curve? Okay. So now we say, look, we actually have our change in velocity, our average velocity, times our delta t. We really have our velocity, oops, over 2 times our delta t, and that's our distance, or our change in distance, excuse me. Right? Or how far we have gone. And the way does everyone understand how we got that, right? Because it's really our velocity final, our velocity initial, right? And it's really that whole velocity change, or final, v final, let's say we started at 0 here, right? It's really our v final times our delta t, but half of that, right? Everyone with me? Okay. So that's how we figure out the delta distance for a constant velocity versus time. Okay? Now I'm going to take this, I'm going to shrink it down. Okay? And now I'm going to draw an acceleration versus time with a constant acceleration. Okay? Here's our delta t, right? And this is our acceleration. So acceleration is equal, what did we say acceleration was equal to generally? What did we say it was equal to? What was the initial equation? Right, over change in time. So acceleration is really equal to, or excuse me, our, if I solve for delta t, well, actually take this, if I said, well, acceleration times my delta t is going to equal what? My delta velocity, right? So this is going to be my change in velocity under here, right? Okay, and so what I can do now is that I can try and figure out, and this is actually, by the way, our this is our change in velocity over 2, right? It's our change in velocity, right? Because it's from this to this divided by 2, right? So if I know that my delta v is equal to this, I can actually plug this guy into here. And I can say, look, delta v, which is really a times delta t over 2 times delta t over 1 equals delta d, right? So my delta d for constant acceleration is a delta t squared times 1/2. And that's how we figure out our distance relative to our time and at a constant acceleration. Again, constant acceleration, constant velocity, okay? Or so both of these are what? Constant acceleration, right? So for both constant accelerations, I can figure out how far I've gone by looking at my acceleration in my time or my velocity in my time, right? Here's my velocity in time. So I can look at delta d equaling my delta v over 2 times my delta t, right? If I just knew the velocity. But if I knew my acceleration, I didn't know my velocity, I can figure out that distance. So here's an interesting thing. Here's where this comes in. If I have a ball, okay, and I drop it, okay, and I drop it a certain distance, okay, if I drop it a certain distance, and I know the acceleration rate that's falling at, by the way, do you know what acceleration rate? Well, why is it going to fall?
Gravity.
Gravity. So gravity is a force, okay, and it's going to create an acceleration, okay? So I have a certain acceleration, right? Okay, the force due to gravity. So let me take that back. Gravity is not a force. Let me take that back. I have acceleration due to gravity. Nuance, but we'll deal with that. Because it really is, it's depending on our objects and how close. But anyway, if acceleration due to gravity, if I know the distance, I can figure out what? How long it will take to fall. Okay? Well, notice something interesting. If I have this object and I have this object, they're both under what? They're both falling at determining. They're both falling because of what? Gravity. And gravity makes everything fall at the same rate. Okay? 9.81 meters per second squared. Well, if I fall the same distance, what does that mean about the time for both of these objects? Yeah, they're going to hit the ground at what? The same time. So if a really heavy ball, you can feel how heavy this is, versus a light thing, what does that mean?
It's defying gravity.
Which one do you think would hit the ground first? That ball, heavy ball. But notice, it doesn't matter.
What about like air?
Okay? And we're going to talk about air resistance in a little bit. It's almost lunchtime, right?
Yeah.
Okay. I want to stop there because that's what we're going to get into. But it's important that you know this. It's important that you know this. All right. Yeah, you guys have a good weekend too.